Good day, sir, and to those who's watching this video, if ever there is, this is me again, Marianiki C. Ramirez, 11th STEM student, for another video for the subject General Chemistry 1. This is the second video that I uploaded, and in this video, I'll be focusing on discussing about the quantum numbers that is used to describe an electron in an atom. So without any further ado, let's get started.
3, 2, 1.
Title: Quantum Mechanical Description of the Atom and its Electronic Structure. Specific topic: Use quantum numbers to describe an electron in an atom. So let's start first by defining what is quantum numbers. What are quantum numbers? Quantum numbers are values that describe the energy or energetic state and position of an atom's electron. The numbers indicate an electron's spin, energy, magnetic moment, and angular moment. According to Purdue University, quantum numbers come from the Bohr model, Schrödinger HW is equals to W wave equation, Hund's rule, and the Hund-Mulliken orbital theory. To understand the quantum numbers that describes an electron in an atom, it's benign to be familiar with the related physics and chemistry terms and principles. Let's start by defining what is the principal quantum number. Principal quantum number. First quantum number that describes the electron shell or energy level of an atom. It is denoted by the symbol small letter n. The value of n ranges from 1 to the shell containing the outermost electron of that atom. The principal quantum number also identifies the distance from the nucleus of an atom to an electron, the size of the orbital, and the azimuthal angular momentum. For an example, in cesium with the symbol Cs, the outermost valence electron is in the shell with energy level 6, so an electron in cesium can have an n value from 1 to 6. Azimuthal quantum number, or the orbital angular momentum quantum number. The azimuthal quantum number describes the shape of a given orbital. It is denoted by the symbol small letter l, and its value is equal to the total number of angular nodes in the orbital. A value of the azimuthal quantum number can indicate either an S, P, D, or F subshell, which vary in shapes. This value depends on and is capped by the value of the principal quantum number. The value of the azimuthal quantum number ranges between 0 and n-1. For example, if n is equal to 3, the possible azimuthal quantum numbers values are 0, 1, 2. When L is equals to 0, the resulting subshell is an S subshell. Similarly, when L is equals to 1 and L is equals to 2, the resulting subshells are P and D subshells, respectively. Therefore, when n is equal to 3, the 3 possible subshells are 3s, 3p, and 3d. The picture shows the combinations of the principal and azimuthal quantum numbers. The magnetic quantum number. It describes the energy level available within a subshell and yields the projection of the orbital angular momentum along a specified axis. that is denoted by the symbol ml. For example, if n is equals to 4 and L is equals to 3 in an atom, there are 7 possible values of the magnetic quantum numbers. These are -3, -2, -1, 0, +1, +2, and +3. The picture shows the shapes of orbitals as per the corresponding quantum numbers. The first column shows the azimuthal quantum number values. The second column is the corresponding number of orbital using the equation 2l + 1, and the third column shows the possible values of ml. Spin projection quantum number. The electron spin quantum number is independent of the value of n, l, and ml. The value of this number gives insight into the direction in which the electron is spinning, and is denoted by the symbol ms. The possible values of electron spin quantum numbers are +1/2 and -1/2. If it's positive, it's spin upward and counterclockwise, but if it's negative, it's spin downward and clockwise. So finally, I already discussed the different terms and principles that related in quantum numbers. So now, let me give some examples of elements and lost electron configuration to describe their electron in an atom by identifying and finding their quantum numbers. So before I go with examples, let me give you first the summary of the discussion and also the rules that you need to remember in answering or identifying the quantum numbers of the element. For the better understanding about this topic, I will give some example. So I have here 3 specific elements: the hydrogen, the fluorine, and the helium. And I also have here the last electron configuration, the 5f13, the 4d4, and the 3p5. I will give the quantum numbers of these elements and the electrons. First, I will give the values of s, p, d, and f subshells so that we can easily find the values of L, ml, and ms. If an electron has a subshell of S, last electron configuration, the value of L is always 0. The same with the value of ml. It's always 0. It has 1 orbital. For the p subshell, it has a value of L of 1. It has 3 orbitals with the values of -1, 0, and +1. For the d subshell, it has a value of L of 2 and an ml of -2, -1, 0, 1, and 2. If we count these values, we can conclude that there are 5 orbitals. For the f subshell, the value of L is 3. The value of ml is -3, -2, -1, 0, 1, 2, and 3. There are 7 orbitals. For for ms, there are only 2 values. It can be either +1/2 or -1/2. you can say that it could be positive 1/2. It spin upwards. You can say that if it's negative 1/2, if it's spin downward. Now, always remember these values because it will be easier for you to understand or to give the quantum numbers of a specific element or electron. Let's give the 4 values of quantum numbers of hydrogen. Hydrogen has a 1 electron. How can I say that it has 1 electron? Because based on periodic table, the value of atomic number is 1. If you still remember our previous lesson, atomic number is equals to the value of proton and electron. Proton has a positive charge and electron has a negative charge. 1 is 1. This is the electron configuration of hydrogen. And its orbital notations. Since it's only 1 and S has only 1 orbital, this is its orbital notation. Let's find its value of the quantum numbers. For the energy level, or the N, how can we find? Just if the electron configuration is present, only look for this. Since it's 1, the energy level of hydrogen is 1. For the value of L, as I said earlier, since it's S, the value of S and L is equals to 0. L is equals to 0. For the ml, again the value of ml in S is equals to 0. For the ms, it's upward, so it's positive 1/2. By looking at this, we can say that it is paramagnetic. How can you say it? Because if we can see an unpaired electron, it is paramagnetic. But if we can see that all in orbital notation has a paired electron, it's diamagnetic. Hydrogen is paramagnetic. Now, for a second example. For the element helium. Helium has a 2 electron. Based on periodic table, its electronic configuration is 1s2. Its orbital notation, since it's 2, 1, 2. The orbital is filled. Let's find the 4 quantum numbers. N is equals to 1. L, since it's S, L would be always 0. ML, the same. If it's 1, and it always S orbital or subshell, the value of L and ML is always 0. For MS, since the lost arrow spins downward, you could say it's negative 1/2. And different from the first example, which is the hydrogen, helium has a paired electron, and it's diamagnetic. For the last element, chlorine. Has a electron configuration of 1s2, 2 S2 and 2p5. That's right, it's orbital notation. The S subshell has a 1 orbital, and the P subshell has a 3 orbital. Since the last configuration electron is P and has 3 orbital, it could be the value of ml could be -1, 0, or 1. 1s2. Since it's 2, the s orbital is filled. The same with here. Based on Hans' rule, fill first with this. If we fill an orbital notation like this, it's wrong. The right way of filling or writing an orbital notation is by filling first the each orbital lead upward, one by one. Then let's go with the word spin. 1, 2, 3, 4, 5. The value of n is 2. The value of L, since it's P, the value is 1. The value of ML, since the last arrow landed on second orbital of P with the value of 0, the value of ML is 0. The value of MS, since it's spin downward, it's -1/2. It has 1 paired electron. 1 unpaired, it's paramagnetic. For example, I have here an electron of 5s13. Based on this configuration, we can make its orbital notation. Since it's F, it has a 7 orbital. 1, 2, 3, 4, 5, 6, 7. The value of the orbital is -3, -2, -1, 0, 1, 2, 3. As I said earlier, let's fill first with upward spin, 1 by 1, per Hans' rule. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It landed on 6th orbital with a value of 2. Let's find its quantum numbers. N, this energy level is 5. L is 4. I mean 3. ML, since the last spin landed on 2, the value of ML is 2. And it's spin downward, so it's -1/2. Since it has 1 unpaired electron, we could say that this is paramagnetic. Fourth example, electron 3p5. Let's write its electron configuration. Since P, it has 3 orbitals. The value are -1, 0, or 1. Since it's 5, let's count 5. 1, 2, 5. It's stopped in the second orbital with a value of 0. Let's fill its quantum numbers. The energy level 3. Since it's P, the L is 1. ml, since the last arrow stops in 0, the value of ml is 0. ms, since it's spin downward, it's negative 1/2. Again, it has one unpaired electron. It's paramagnetic. Let's go with our last example. Last example, we have 4d4 electron. Since it's d, it has a 5 orbitals. 1, 2, 3, 4, 5. The value for ml is negative 2, negative 1, 0, 1, 2. Let's count 4. Let's fill first each orbital with upward spin. Let's count 4 since the value or the numbers of spin is 4. 1, 2, 3, 4. Let's stop here in 4th orbital with a value of 1. Let's find its quantum numbers. For N, the energy level is 4. The value of L, since it's D, it will be always 2. And ML, since it's landed on 4th, with a value of 1, the value of ML is 1. MS, since it's been upward, it's positive 1/2. Since all the electron is unpaired, we could say that it is paramagnetic. So, that's it. Just remember these values, and you could be able to identify the quantum numbers of a specific element and electron configuration. Using the values of quantum numbers that I get, we can describe the electron in an atom. So here is the 2 examples and their values of quantum numbers. Let's describe the electron in hydrogen atom. The energy level of electron in hydrogen atom is 1. Its subshell is 0. The energy level available within a subshell and yields the projection of the orbital angular momentum is 0. And its spin of electron is positive 1/2. For 4d4 electron, the energy level is 4. The subshell is 2. And the energy level available within a subshell and yields the projection of the orbital angular momentum is 1, and the spin of electron is positive 1/2. So this is the ending of my video reporting. I hope that I explained it explicitly, and thanks for watching.